There is a problem?
I can try, I can do it here. I can do it from the computer. Okay, so it's, yeah. The pointer works, so that's a bit.
The pointer works?
Pointer does work, but not the editing of the slides. So I will focus on soils to start with, and we talk about VOC emissions, so release from ecosystems to the atmosphere, but I turn it a bit upside down. So I tell about how we've observed that the terrestrial ecosystems, and I believe also the aquatic ecosystems, also take up these gases from the atmosphere. So it's not just a one-way road. I will approach the aquatic systems at the end, and then Michael will take you further into the aquatic systems. So soil is a little bit like a black box in the business of understanding the volatile organic compounds. And the research has largely focused on plants. So it's already well known that plants, especially trees, release large quantities of carbon as volatile organic compounds in the atmosphere. So something like 1,000 teragrams of carbon per year. And that is the largest source of volatile organic compounds. About 90% is released from nature, contra 10% from anthropogenic sources. So then we've been wondering, okay, is it only plants or do soil also play a role and soil microbial communities? And we know that VOCs are released also from plant roots. And we expect that also soil microbial communities would contribute these different gases to the pool of volatiles. And the research into the soil processes and soil emissions has been really active. So there's been a lot of studies trying to quantify the release of volatile organic compounds to the atmosphere. And yeah, I was a bit wrong when I said in the beginning that I'll introduce what the volatile organic compounds are, because I can see I didn't have any slides on that. Do you know what the volatile organic compounds are, or do you need a short introduction on that?
Yes, we need that, I guess.
Yes. So you work with, or you've heard about the processes related to CO2 and methane, maybe?
Yeah.
Yes, that's more familiar. So the volatile organic compounds are organic gaseous molecules that are released from nature, and they are usually larger molecules than methane. So methane could be one of the volatiles that we talk about, but it's taken separately because it's a greenhouse gas, whereas volatile organic compounds react very fast in the atmosphere. They are reactive gases that have climate feedbacks that are different from greenhouse gases. And maybe Michael will come into those in his talk. So the smallest molecule that I talk about in this talk is methanol. And then the largest, I believe, is sesquiterpenes, which have 20 carbon atoms in the molecule. So there are thousands, perhaps 30,000 different compounds in the group of volatile organic compounds. So it's a really diverse group of molecules with different ecological roles in communication and signaling, defense against abiotic and biotic stresses, and then they also have different atmospheric implications because of the high reactivity atmosphere. So then back to the soils and the role of soils in this. And I will tell a little bit about one study that we did in Rinnan. So we have this site where we wanted to study how different plant species might they also affect the soil VOC concentrations, because we know that plants are a really important source of VOCs. So we measured concentrations in the rhizosphere of the soil, so these plants, and over 3 years. And some of this variation that we observed could be actually explained by the plant species. So we could see that averaged for all the measurements, we had different profiles of volatiles, here categorized into different chemical groups under the different plant species, and some had clearly lower concentrations in the rhizosphere than other species. So there was some explanation by the plant species, but then in a second part of this same study, we sampled along a transect in the area, which started from this semi-desert area with hardly any plant cover, and then it led to this vegetated tundra. And sampling along these points showed that if we compare, for example, here, these hotspots, they were totally different. So the number one, you can see it here, had high concentrations, even though it had very low soil organic matter content and low plant biomass. And the site here, number 7, it had high plant biomass and much more carbon in the soil. So we could say that, no, it's not really vegetation cover that can explain the emissions. And we believe that the reason for this is that when we measure concentrations or net emission rates, there are factors that affect the processes that run both directions, and therefore the net result is difficult to explain. So we might get the same net emission rate of 1 with very low production rate and low consumption rate, and high production rate and high consumption rate. And this is something that we really don't understand yet. There are many processes that affect these gases in the soil environment. The production processes, the degradation and transformation processes, and also changes between VOCs being in the gas form and being dissolved in the soil water or absorbed on soil particles. So it's complex, and measuring the net concentration is a little bit meaningless. So then let's try to look at the VOC uptake in soils, which is something that we've put more emphasis on lately. And I tell a little bit about another example study that we conducted with soil samples collected in 2 Danish ecosystems, a beech forest and a heath, coastal heath ecosystem, very contrasting sites with high nutrient content at the beech forest, and then low nutrient content and dry soil with a lot of secondary metabolites here in the heath ecosystem. And what we did was a laboratory study where we had glass containers with soil, and then we had this flow-through system measuring the volatiles in real time with an instrument that can measure all the volatiles at the same time. And then we added either nitrogen to have anoxic conditions or synthetic air, and we added some VOCs into the air that went in. So we added a mixture of these different VOCs from methanol to linalool, which is an oxygenated monoturbine. And we had 3 different concentrations that we added, and then we also had a no addition treatment. You can see the concentrations here were at ppb level. And so what we could then see on the screen of our instrument was this kind of time series. If we didn't add any VOCs and we had the glass jar with soil versus an empty glass jar, we could see that there were higher concentrations in the soil jar than in the blank jar. for the different compounds that we measured. If we added VOCs, then the situation turned the other way. So we had higher concentration in the plant chart and lower concentration in the soil chart. This aren't working, so now I'm free to move away from the computer. Can everybody still hear also on the Zoom if I move here? They will complain if not. So this is how everything looked like. So a tidy drawing, but in reality it looks a little bit messier. We have an incubator where we can control the temperature. We have a valve system that opens and closes so that we can have a semi-automated system where we measure different samples in real time. And then let's look at what we found out in this experiment that was published just at the end of last year. So when we didn't add any VOCs, then soil was indeed a source of VOCs. And when we put all the hundreds of compounds in a principal component analysis, this is how the results look like. So we can see that the different locations, the forest and hill, they have different mixtures of VOC released. And we can also see that the mixtures are different if we have air or if we have nitrogen as the headspace gas. So if the conditions are anoxic or oxic. So there are differences in what is emitted. And these are the emission rates at the no addition level. So we could see that the emissions are actually higher from the nutrient poor soil, which has more secondary metabolites. And that the emissions were higher with nitrogen as the headspace gas for many compounds. We also could see that the emission rates were temperature dependent, which is not a surprise because, of course, the processes are temperature dependent, the biological processes, and also the volatility of the compounds increases with higher the temperature. So then, what about then if we add VOCs to the headspace air? Then this is a complex graph showing all of our target VOCs that we added to the system. And let's just zoom in a little bit to have a look. So we have the three different VOC addition levels. So low, medium, and high. And then here we have the emission rate of VOCs. And acetone was the only compound that was still emitted from the soil, even with acetone being added to the headspace. But you can see that the more acetone we added, the lower the flux became. So the uptake rate increased when the concentration available increased. For most compounds, it looked like this. So this is an example for isoprene. So the uptake rate, it increased when we added more isoprene to the headspace. And yeah, so now that we go to this direction, it means that there was net uptake. So if we now measure this in the field, we would get zero net emissions. And the uptake rate was also temperature dependent. So if we added the same amount and measured at different temperatures, there was higher uptake at higher temperatures. So was this really microbial activity, or was it just some absorption to the soil particles? We would very much like to have a nice sterile control in these experiments, but both autoclaving and gamma radiating soil samples is very difficult. So it leads to really huge release of VOCs from soil. This is probably because of the dead microbes releasing all the carbon and then all this labile carbon being transformed into different volatiles. We used in this experiment sterile glass beads as a very simple control, and there was very low uptake on this, so it was non-existent. So it seemed very much being a microbial process. And something a little bit more sophisticated to tease that apart is using isotope labeling. So in an earlier study, we have used 14 C-labeled VOCs that we purchased and then incubated them with soil in containers where we have a vial with CO2 absorbing liquid that then absorbs the CO2 produced from the degraded VOCs. And then we can measure the radioactivity on a liquid scintillation counter. So in these mineralization assays with different molecules that we've been able to purchase, not all the VOCs are available isotope labeled, unfortunately. We measured then this accumulated mineralization rates, how much was turned into CO2 at different time points. So here it's up to 150 hours. And for all compounds that we measured and with all soil samples we've tested, there is this active mineralization of the compounds. The points that you see here on the x-axis and with 0 values on y-axis, they are sterilized soil. So here where we actually don't measure the VOCs but CO2, we can sterilize the soil and we see that nothing happens in those soil samples. So it is an active biological process taking place. And an interesting observation here is that this mineralization rate is higher in soil samples that come from environments where the tested compound is more abundant. So it kind of links to the results of the previous study I told about. So we have higher degradation rates of the VOCs or uptake rates, as you wish, if those compounds are readily available in that environment. So then this question, how large source is soil for the ecosystem VOC emissions, we have turned it a little bit around and are wondering how large sink is the soil for the VOCs in the environment. And we think that it's really important to try to understand these processes better so that we can actually model the processes and add these processes to ecosystem models. The soils are currently not included at all in any way. So we are working with the data to first start with plant litter decomposition to add those processes in ecosystem models, and then trying to parameterize the soil production and consumption processes so that those can be added as well. So in the experimental work, we are continuing the use of isotope labeling to tease apart the production and consumption processes. And there are many questions still to be studied about the effects of different environmental factors and also biotic factors, and then the understanding of who is doing what in these processes. So we are coupling metagenomic and transcriptomic studies also to these process experiments. And then I'm going to finish with just a little bit about the aquatic areas. So we've done one larger fieldwork campaign in a permafrost affected peatland here in northern Norway, where we did measurements along this transect from chalsas, which are these elevated mounds with permafrost in here, And then they thaw. There's this dynamic landscape where they thaw, and then the ground collapses and forms thaw ponds. And we measured both at this bare soil palsa, vegetated palsa, on this thawing slump area, and then in the ponds, both in non-vegetated and vegetated areas. And the measurements were done without plants being present, so it's soils and water measured in these soil respiration collars with cartridges that were then taken for GCMS analysis in the lab. And what we found was that there were large seasonal differences that I'm not showing here, but then also that there were emissions from all these different surfaces, highest terpenoid emissions, which these are interesting, these sesquiterpenes, monoterpenes, and isoprene, because they have really large or much studied atmospheric impact. So they were largest here where the permafrost is actively thawing. The emissions were lowest from the ponds, and that is probably because the diffusion of the gases is slow in water. So it might not be that there's no production there, but during our measurements, the emission rates were lower. We could also see that the mixtures of VOCs that were released, they were different in the different landscape types. So this is the vegetated thaw pond, and that was the most different one compared to the rest. But then the thaw pond, the green one, was more similar to the vegetated pond than to the other soil surfaces, and then they were kind of here partly overlapping. And the September separates for all of these here. So we've also done some measurements on subarctic fen and lake area using a method where you measure concentrations in tower. And here in this kind of landscape where no trees grow, we can have a very low tower, only 2 meters high. And then the measurements from here, they are taken with an instrument that is here inside this tarp covered shed, and with calculations that take into account 3-dimensional wind, we can calculate the net fluxes between the whole ecosystem and the atmosphere. And so this was one of the scariest moments of my research life so far, where we transported the expensive instruments to the field site, and then it was landed very nicely with the helicopter. Nothing bad happened. And then we were building this shed around it. And here is the tower by the lake shore with the installations for the wind measurements and the gas measurements. And then inside the shed, even though it looks really quite horrible from the outside, we had very sophisticated instrumentation taking care of everything. So we did measurements in real time over a growing season. And so the site had a nice footprint area where half of it is on a peatland and half of it on a lake. And we measured so that we could compare July and September with high solar radiation and higher temperatures in the mid of the growing season in July, and then low temperatures and solar radiation in September. And the results for lake and fen, so the peatland area, are shown here. So you can see that for the different VOCs listed here, and there's some greenhouse gases and water fluxes also shown. The lake, for example, emitted isoprene, dimethyl sulfide, and monoterpenes and methanol. but most of them were at lower rates than the Venn area. And then it was seen for some compounds, some water-soluble compounds. So these negative fluxes mean that the lake was actually taking these compounds rather than releasing them. And this is work that we will continue even more. Now we are starting a new research center that focuses on different volatiles that are exchanged between ecosystems and the atmosphere. So in this Center for Volatile Interactions, we study the production and consumption and emission processes of different volatiles in soil that I told about, but also in plant phyllosphere and rhizosphere, in mosses and lichens, and in aquatic environments as well. And in connection with that, we've started by doing some simple measurements with floating chambers to study the water atmosphere exchange, as well as doing sampling in the lab of different cultures and water samples, both immersed in water as well as in the headspace. And also here we are, because of this new work, it's a nice collaboration with the local researchers, Genevieve, and with Isabel and Michael, who will present next. So we will hopefully find out more about the volatile exchange in Lake Geneva in the coming months. So with that, I want to thank you for your attention.
Thank you. Is there any question? And also we'll have some questions from the people that are online, but is there any question in the room?
Yeah. I wonder, I think it was really interesting, thank you. I'm not involved so much in science nowadays, but I was interested in how do you know how long the volatiles will stay in the soil yet? Because you made really short-term experiments and you saw that they were absorbed, but have you got an idea how long they can be absorbed for, and then will they be released, and will they be the same component? Obviously not, it probably has changed. So
Yeah. That's a really good question. So it probably depends very much on the compound, so how long they will stay. So we did these experiments where we used isotope labeled compounds, and for simple compounds like methanol, we can hardly measure it. So we did the experiment at 6 degrees, so as quite low temperature. It was soils from cold areas. And things were happening so fast that we could hardly keep track. So, but for more complex molecules, things are slower. We also tested these processes in permafrost soils that were thawed. So soil that had been frozen for thousands of years, and the microbial communities also being a little bit asleep for a long time. And it took 3 days, and then things started to happen. So the activity seems to be there, I think, in all soils. That's my guess. So I think it depends on the microbial communities and what they are used to. And that's kind of what our studies are hinting towards, that there is like the communities are evolving as whatever compounds there are available for them to use as a source of carbon and energy.
I'm sorry, I don't understand. I don't know anything about the VOC. And thank you for your very interesting presentation. And I have one question about the VOC compound. So do you have an idea of which VOC compound that the majority that has a biggest fraction of emission, and then each compound can be used as a tracer of each type of soil, each environment.
Right. That's a really good question, and if you should remember one VOC from today, I think isoprene would be a good starting point because it is one of the most emitted compounds. It might be the most emitted compound. Also, methanol is emitted in really high quantities. The problem with methanol is that we don't catch it with all of our commonly used techniques because it's too small molecule. So in micro, we work mainly with in the field with measurements where we catch compounds that have 5 carbon atoms and up. So we might miss some, but isoprene is emitted at very high rates, perhaps even half of the 1,000 teragrams is isoprene. And then you asked also, was it like what are there some example compounds that are important in different types of systems? So then in aquatic environments and marine systems, sulfur compounds are also really important. So DMS is another good one to remember. Maybe Michael will talk more about those compounds.
So, yeah, Riikka, thanks so much. Really good talk. There's so much interesting work from your group. It's impressive. I start at the end of your presentation, or towards the end of the presentation. You mentioned the work where you looked at different soil types and the ponds, the thaw ponds in particular. When you said thaw ponds, did you mean sediment or did you mean water? That was the first question to really lead into the next question.
Yeah. So it was these soil respiration like collars or bases that are used for the measurements. So they are put in the sediment, but there is water in them. So there are holes so that the water level is the same as in the pond. So
it's not the sediments in the pond.
Yeah.
It's the water that is in the pond, basically.
So there is the sediment and then the water.
Okay.
So both are in the measured area.
And then you showed that there are differences, obviously, between the pond and the soil.
Yeah.
How would you describe the microbial activities? Would you think that they are higher in the terrestrial environment or higher in the aquatic environment?
Yeah, and that's a really good question. I think a lot of the VOCs that we measure are produced in the anoxic processes.
Yeah.
So many of them are actually related to fermentation. And then, but I was surprised to see that also the vegetated pond was emitting terpenoids. So there were also some sesquiterpenes and so on. So I don't know if those are then produced by some microalgae in the water or if they are plant roots, because that was now the vegetated. There was no plants in what we were measuring. So I don't think terpenoids are coming from the anoxic sediment. So that's some more photosynthesis related processes behind those.
And then now that you mentioned anoxia, I come back to your experiments that we did with the PTR-12MS on isoprene, where we added nitrogen gas to encourage anaerobic processes. And then the isoprene went up. Why is that?
Yeah, so we didn't really truly have a long-term anoxic conditions. So the soils were not kept under anoxic conditions. It was just using different headspace gas. So I think what we've been doing there is just creating perhaps some anoxic microsites at the surface of the soil. I wasn't truly comparing anoxic and toxic. So I think we would have needed to have like a long-term incubation to show that. So I think, yeah, if you read the publication, that was something we were really wondering, how should we put it, because the results were a bit puzzling with regard to that. We would also, I think I would expect that the oxidation of the compounds is an oxic process and not anoxic process. So yeah, but I know that methane oxidation is also very active at the kind of at this interface between oxic and anoxic conditions. So perhaps it's the same for these,
Yeah.
yeah.
But is the paradigm still that isoprene production in general is driven by photosynthetic processes? Or would you say that heterotrophic bacteria play such an important role in soil for isoprene production that there are other processes?
I think I'm kind of thinking it's more the photosynthetic processes, but I don't know enough about the heterotrophic part of this thing. Yeah. Right?
Yeah, so in the study that Michael mentioned about like the actively thawing areas, you said that the largest VOC emissions were in the areas where the permafrost was like actively thawing. Do you have an idea why? Is it because of like the micro communities that were kind of like awakening and starting to produce VOCs, and is it because they're so ancient as well? Or yeah.
Yeah, so it wasn't the VOC emissions of like the total VOCs were not highest there, but of terpenoids. And I don't really have a good explanation. I know that from the lab incubation studies where permafrost has been taken in glass jars and then measured while it's being thawed, both by my group and another group at University of Helsinki. Both of these studies have shown that permafrost is emitting very large amounts of VOCs. But then in our studies, we showed that most of those VOCs are consumed during the transport towards atmosphere, so they wouldn't reach the atmosphere. But on this like thaw slump area where it's the permafrost is degrading and the soil is collapsing, so there is perhaps less transport route, so the gases that are released from the permafrost might be easier released to the atmosphere and not taken up by microbial communities. So that might be the reason in this balance. Yeah.
Yeah, I wonder if ebullition could play a role in these conditions. Have you ever measured VOC from the bubbles escaping from the water bodies?
Not yet. Well, these floating chambers studies that we've done are really just one master student has done some measurements, and we are not able to separate ebullition from diffusive transport. So there was the measurements that we took for VOCs here were not online measurements where we would see if there was ebullition. So it was a measurement over a long time where we pass through air through this sorbent cartridge, and then we just get one value for the whole measurement. So we don't know it's including ebullition if there was any. We were trying to avoid that bubbles would form when we were placing the floating chambers at the shore. Yeah.
Do we know if there is a gradient of box composition along with the depths in the soil? Is it related? If yes, is it related to the degradation up to the emission of the atmosphere?
Yeah, so we have some ongoing work where we collected soil samples at different depths, I think down to 70 centimeters. And yeah, there is. So it's there is a difference, and all the activities are highest where we have the higher microbial community. So usually in the topsoil. So in this study, I don't remember the results exactly, but we are measuring also consumption. So it's a bit the same setup as in one of the studies where we added different concentrations. And I think the uptake rates are lower in the deepest layers, and also the production rates.
Questions online? Online, whether there are any questions?
Isabel?
Oui, est-ce qu'il y a...
Yeah, is there any question for the people in the Zoom link?
I have a few ones, but maybe I limit myself for later. But I was wondering, I was puzzled by the activation of consumption as when you added the VOCs. And do you think that these are the dormant bacteria that are there, and when they have the resource are taking it, or it's just that they're using something else, that they're polyvalent, or is, and also second part is there any work that have identified on the gene where the VOCs are produced and can identify more precisely who are responsible for which VOCs or in general?
Yeah. So if I start from the last part, so there is quite a bit known for isoprene oxidation. So that's something about who is doing it, and also about the genes involved, and so on, the enzymes and so on. And there is also some co-oxidation of some compounds, so it could be that methane oxidizers might also play some role for some compounds similar to that. But I think for the vast majority of VOCs, if we think about the whole large spectrum of thousands of different compounds, we don't know exactly who is doing what. And yeah, so that's something I think we will try to dig into. Of course, it's difficult to cover everything, but we'll try to look at some of these, some of the compounds in collaborations with experts that are doing this kind of molecular work. And then for your first question, which was
like increase of consumption
Right.
when you put.
Yeah, so it seems to be that that's pretty much whatever you add, it will be broken down or consumed. Yeah, I don't think we know anything much more about that yet. So these have been really simple process studies, kind of following the tradition of how people did for studying methane cycling 30 years ago. So we're kind of following on the footsteps with a little bit more difficult gases that we work with, but yeah, trying to do similar work. So I think it's a little bit like a black box for us, but we know that it's microbial, not just abiotic absorption like we've often been asked from the reviewers. Yeah.
Okay, so we can switch to the next presentation. Thank you very much, Riikka.
Yes, thanks, Riikka. It's really nice presentation. I have some questions, but I will ask you after.
Okay, Genevieve.
Okay.
What do we have to do here? Stop this and then get minor? Is that what I do? Or do I just bring this one up?
Yeah, I think you can just start, yeah.
Yeah. It's a lot of empty slides.
I didn't like.
Do I stop this and start again?
Yeah. I'm really bad at this.
Maybe we just like try the first silent. It is kind of scary. It's just.
Oh, here we go.
Is that-
This is the stuff.
Yes. Here it's.
Oh, that's good. That's fine. That's fine.
Yeah.
Good. So as long as people online, no, I stopped the shit out of it. Is it still on?
You need to share again.
Oh, no, it's. Just share the screen. It's here.
So I'm hoping that
This
people
is good for us.
are able to see the first slide.
Yes, it's good.
Good, and this will hopefully disappear.
It will, yeah, it should disappear.
It works.
Yeah.
It works.
Good. Fantastic.
Sorry,
great.
is it just possible to turn the camera or not? Because we only see the roof. So we don't see.
What camera are you talking about?
The,
Yeah, just to
Oh, that one there.
the
That's-
camera of the computer.
Yeah. Is that this one?
No, it's the one that you were, there is your
Oh,
presentation,
computer.
Michael.
Okay.
not this?
Ah,
All right.
good. And more to the other side.
Like that?
Thank you. Thank you.
Okay, good. Great. Good, well, bonjour, good morning, everybody. Very nice to be here today and present some of our work to you and some of our plans as well, I think. Once again, my name is Michael Steinke. I work at the School of Life Sciences at the University of Essex in Colchester, England. And Monica is my wife, she's in the audience here. We were just thinking about how long we've been in the United Kingdom. It has been 27 years now. And I believe 18 of those at Essex. And originally we were both from Germany. My degree at the University of Bremen in northern Germany. So I've been studying certainly volatiles, particularly dimethyl sulfide, for much of my life, actually. So the first part of my talk will focus on the smell of the sea, which is generated by dimethyl sulfide, how that influences our life. But I really want to start off with a brief acknowledgement. So rather than having my acknowledgements at the end, how do I move forward?
The space bar or the arrows?
Yeah, none of them work.
And the other,
No.
oh, it's that again.
You have to click once on the presentation, like with the, take the mouse and then it started working maybe afterwards.
Mouse, okay, good. Mouse click seems to work. Let's see how we get on. So once again, I want to start really off with some acknowledgement. All of you here at CARRTEL have been absolutely fantastic in the last 2 weeks. You've been very generous with your space, giving to us, with your time giving to us, assisting us with all the little problems, mini crises that we had, particularly in the last few days with instrumentation. I want to mention Didier, Viet, but then there's also Pascal and Laura who assisted us. Mathilde has been great in the lab. She made lots of space for us and never got annoyed with us yet. So I'm hoping that we'll continue like that. So thanks very much. It's a great opportunity for us to be here and share the space and this time with you. It's a lovely summer for us, and hopefully that will continue along in the future as well. So I just wanted to get it out right from the start. So why are we at CARRTEL? And I drew that very quickly this morning, just to think about, you know, where is it? Where's that scientific overlap? And what you can see here is a little Venn diagram showing Isabel and Riley, then Genevieve and Elora, I think it was, Riikka and Hélène, and Michael and Alex. So these are the 4 different teams from different parts of the world. Isabel from Canada, from Quebec, Genevieve from here, Université Savoie-Mont Blanc, Riikka from Copenhagen, and Alex and I from Essex then. So where's that overlap? And I think this is sort of where what I came up with this morning. There's some people interested in N, which I refer to as the North, you know, Arctic environments, cold environments, and a bit of P as well, photosynthesis. You know, most of the ice cream, for example, is produced by photosynthetic processes, we believe. So all of that is very important. Isabel studies photosynthesis in the lake water, so that's the phytoplankton and cyanobacteria, and Riikka is a little bit more interested in the trees and shrubs and little cryptogamic organisms, I guess, in these boreal forests and tundra environments. And then down here, I've got Riikka and Ellen again, and myself and Alex. We're interested in VINM, volatiles, isoprene, but also methodology. So Riikka has a whole tool she already presented to you of methods available in Copenhagen, which are really quite interesting. I want to learn a bit more of that. And I know a little bit about measuring gases, particularly in aquatic environments, which is sort of an additional challenge maybe to just measuring, I say just, measuring volatiles in the atmosphere. So there's some interesting overlap there. And then Isabel and I, we really want to get some aquatic work going in the north. So Isabel is really good in going out into the North Canadian lakes and ponds and permafrost that is melting away to study these sort of environments. And I think the ultimate goal for us, the playing field, is this area here in North Canada, but also northern Scandinavia. The blue patches here on the map, they show the level of linicity, the lake area density. So we see that the further north we go, we've got areas with incredibly high abundance of water, surface water. The linicity is very high, up to 50% in some parts of Canada. So relative to the terrestrial environment or terrestrial processes, these are areas where lakes, where freshwater systems, freshwater bodies are incredibly important to influence whatever is coming out from, let's say, the surface of Earth and going diffusing into the atmosphere. So for volatiles, it's really interesting area. And that's also an area of extreme rapid climate change. Things are changing so rapidly over the next few decades. That's really a new, I wouldn't call it a frontier, but it's a new playground that is opening up for us there, where we know very little about what the driving process might be that then result in changes in the atmosphere locally and globally as well. So I want to start off in my first part, where I introduce to you a little bit of my marine work, marine gas work, gases and climate, I call that. And I want to start off with this schematic drawing here, which encapsulates much of my work over the last few years. There's the microbial environment all the way on the left, and then microscopic organisms on the right here. You can probably recognize some penguins, a seal, an albatross seabird flying here, and somewhere in between, there's a lot of activity there that results in the release of these volatiles, gases that are produced through biological processes. There's also day and night, day cycle, there's some clouds here. Some of the gases, or one of the gases particularly well studied in the sea, in the ocean, is called dimethyl sulfide. It was mentioned by Riikka already. It's very simple C2 compounds, which you all know. You may never have heard of it, dimethyl sulfide, but you all know it as long as you've been somewhere to the beach, to the ocean, as a typical smell of the sea. Whenever you go to the sea, and particularly at low tide, when macrophyte seaweeds are exposed to stressful environments, they start to release that DMS, a typical smell of the sea. Right? So you all know that compound already. When we look at the globe, although there is a lot of terrestrial environment on there, you will all recognize parts of Africa and Asia and Europe, of course, on this map. But if you turn the globe around, you see that we really truly are a green planet, right? There's a lot of sea on this planet. And although some of the processes are happening very slowly and at very small rates, due to the simple sheer area cover that we have on this planet by water, they're extremely important for everything that happens in the atmosphere. So even small processes can have a dramatic and substantial impact on atmospheric chemistry and on our climate as a result. So dimethyl sulfide is this gas here. You see the molecular structure on the top left there that I've studied for many decades now, 2 or 3 decades already. Started off with working on this for my PhD, maybe even for my master's thesis, can't remember exactly. So aquatic organisms, particularly photosynthetic organisms, particularly when they get under stress, in this case light stress, the sun is out, they start releasing DMS into the water. Just by sheer diffusion, some of that DMS diffuses into the atmosphere. These are little molecules in the atmosphere there. And then due to further chemical processing, we can find that the particles that are produced from that sulfur molecule in DMS, we get the formation of new particles, so-called condensation cloud nuclei, that then attract water molecules to the surface. So whenever a water droplet is formed in the atmosphere, it basically needs a little crystal piece of dirt for the water molecules to adhere to then build a droplet, which then creates a cloud and eventually may fall out as precipitation. So the water is being attracted to that sulfur, the new particle, and many of these water droplets, aerosols, create clouds, which obviously have an effect on our weather. So one philosophical question early on in DMS research was, can algae make their own weather? When they get under stress, light intensity is high, temperature is too high, do they produce more DMS to then influence the weather, the cloud formation, and hence they get some shading? This is what you can see sort of in this satellite image. You see the southwest of England here. This is part of Cornwall and Devon. Plymouth is somewhere here. That's Land's End. And the whiteness in the water here, that's the channel. France is somewhere down here, of course. The whiteness in the water is the reflection of light from a particular algal bloom, from a coccolithore, a calcium carbonate forming microscopic single-celled phytoplankton, which reflects a lot of light back into shades, which we then can see on the satellite image. And these coccolithores, particularly in the Rinnan, they're incredibly good at releasing DMS. They make a precursor. The direct precursor for DMS is called DMSP, or dimethylsulfonium propionate, DMSP. And they make a lot of it. And curiously, there is some indication of some cloud, streets of clouds in this otherwise, crystal clear atmosphere on that day. Happens very rarely in England. You get these, formation of clouds right above it. I mean, obviously, that might be due to lots of different reasons. But I wish to believe that probably the DMS that comes out of this algal bloom had a direct influence on the formation of these clouds. There's on the right, there's an example. The coccolithore Rinnan, which was the main producer of this particular bloom here. So the question then early on already, and this dates back to 1987, probably was the seminal paper by Charles and Lovelock, Andrea and Warren, CLA&W, who came up with this claw hypothesis. They said, well, if we've got, biological production of this gas, DMS, that we can measure, and that's then forming more clouds, it has an effect on the radiation budget, the temperature, and climate feedbacks. How does that then affect the temperature, light, and nutrient distribution in the water? Does that have an effect on the seaweed or on the algae as well? So is that climate feedback that that can be described as part of the Gaia hypothesis? So it's CLAW claw. One of them is Lovelock, and he is the godfather of the Gaia hypothesis, who says that the Earth functions like a self-regulating organism, basically. So he used this as a prime example of how Gaia could function. So they suggested this, and that has spawned a multitude of research activities, really, over the first few decades, then, since that seminal paper in 1987. So the question then is further, then if we've got other processes kicking in, CO2, global warming due to anthropogenic release of CO2 into the atmosphere, what effect does that have? To study that, a few years ago, we went to this facility in Norway, used the European Bergen mesocosm facility there, basically a floating platform that you can see the mesocosms attached to here. And in that fjord that we worked in, they've got these regular blooms of coccolithores, particularly in the Rinnan. So strong area for the production of DMS as well. They can be set up in parallel, but then we can manipulate them. We can manipulate the CO2 concentration or the amount of nutrients that they receive, and then stimulate certain processes. We can spend a month monitoring that in succession. It was quite a few years ago, was one of our students at the time. But then use gas chromatography, and that's an instrument which is probably the same, or at least very similar. No, it's not the same instrument that we have upstairs in the lab yet. It's the same model, but it's a different instrument that we then bring to the site and measure our gases. So this is something that we've done many years ago already, very similar to what we're trying to attempt here at Lake Geneva as well. Gas chromatography that I use is relatively simple. We use what's called a flame ionization detector, a very common detector on many GC systems. This has a disadvantage that we cannot directly identify these compounds by their molecular mass. We do not have a mass spectrometer detector on there. but it has the benefit that these instruments travel a little bit more easily, whereas a mass spec wouldn't travel quite so easy. So the idea is you can set it up for a few weeks, do some measurements, if you're lucky, and then get some good data with that. That gives an indication of the process going on. And this is just a schematic of how that works. I don't want to give you too much detail on it, but the exact system that you see on the left here in this photograph, that's what we have set up here in the lab at Lake Geneva at the moment. This is another mesocosm experiment that we participated in. These are free-floating mesocosms, so trying to go more into the open ocean environment rather than into a fjord system, much larger systems as well. That was a lot of effort that we spent over the years studying. And some of the very first data, they were worrying in a way. So what we see here is we've got the data for the mesocosms in Bergen in two different scenarios here. One is the ambient CO2 and one is the high CO2 environment. And we see, although we get a nice development of the bloom with high DMS concentrations shown here along the y-axis, in May, we get the output of DMS quite nicely, which can then stimulate clouds and lead to cooling because clouds often they shade the planet. Whereas in high CO2 mesocosms, the amount of DMS that was released was suppressed. And that's worrying because it suggests an accelerating warming scenario where we end up with less clouds in a higher CO2 environment. We've done a whole range of those, and the outcomes are sort of mixed in a way, but quite often the amount of DMS and DMSP, which we see on the left and in the middle here, that's the data for DMS for the different years, DMSP for the different years. The black lines here, I think they are the ones that refer to the high CO2 environments. You typically see that there is slightly less in many of those experiments. So that's worrying in a way. I then went on with a master student to do this little study where we combined the factors of temperature and CO2 in our experiments. And sort of luckily, in a way, we see although the effect is there from the ambient DMS production at this level here, when we add CO2, it goes down. When we increase the temperature, it sort of stays the same, but with temperature and CO2 together, that's compensated. So if we're expecting both an increase in CO2 and in temperature, the ultimate outcome likely will not be quite as dramatic, i.e. there will still be a similar amount of DMS being produced by Emiliana Huxley in this particular case. So that gave us some hope that things are not going apocalyptic quite too quickly. But it's an interesting sort of little exercise to consider for modeling of future climate scenarios. So I want to summarize the first part of my talk. DMS is climate cooling the main trace gas. I introduced you to that. The ocean has an average DMS concentration of relatively small amounts, 2.3 nanomoles per liter only, and releases, as a result of the large area that it covers, about 27 teragrams of sulfur per year, right? And that's in the form of DMS. So it's a huge amount of DMS that is coming out. Now, this DMS, when it comes to cloud formation, will not have an effect on the environment here, but it does have an effect in remote ocean areas. So when you think about the Southern Ocean, there's very little land mass, huge, Pacific parts. There's very little dust from deserts, no cars driving around, or very few. Many of the clouds that are formed in that areas, they exclusively stem from the process of sulfur generation of new particles in that atmosphere. And the DMS is the main driver of that. So it has a huge effect on the climate locally. Increased CO2 results in decreased DMS, but the combined effects of increased CO2 and temperature results in unchanged DMS. So that was an important study for us to really do. Okay, now I want to switch over and move to the freshwater system. I want to introduce you to one study that we've done in a very similar fashion a few years back at Lake Constance in southern Germany. Very similar thing. Steinke rolls up with a few instruments, sets up in the lab, gets things going, trying to measure a few things, exactly what we are doing here. And we've done that a few years back at Lake Constance. We published that in scientific reports in 2018, if you wanted to take a full look at that. This just gives you an overview or a map of the Lake Constance area that we worked at. So these are the stations here. The dots that we studied. There's site 1, sort of long-term observation site for Lake Constance. There's site 2, which was much closer to the shore here, and the location of meteorological stations in as well. So we quantified the vertical distribution of isoprene and DMS in depth profiles, total concentration surface samples, and calculated flux over a diurnal cycle, and then also looked at the DMS and isoprene production in 10 different species of freshwater phytoplankton. And here's some of the data. It's a bit small, but I think you will get the message. There's temperature on the left here for the different dates, 3 different depth profiles, weekly depth profiles, the data for isoprene, the data for DMS, and then some chlorophyll data, and also some information on the pigment composition in the chlorophyll using the fluoroprobe instrument. So you can see quite nicely was, in July was a lovely summer, lots of sunshine, you get stratified lake surface water, and then with that stratification, you get an increase in both isoprene over time and also an increase in DMS. The fact that there was noticeable amounts of DMS in the lake surprised me in a way, because there's little understanding about processes that lead to DMS formation in freshwater systems in comparison to marine systems. So that was interesting right from the start. We then did some linear regressions with the fluoroprobe data to tease out a little bit, what are the main contributors possibly to these processes. So the colored numbers here, they show you the good probabilities, I guess. So when it comes to isoprene, we get good overlap with stronophytes and chlorophytes, and the total chlorophyll as well. Whereas with DMS, we get overlap with chlorophytes. So it gave us some indication from the pigment data. What are the organisms, the groups in total diversity of the phytoplankton that may contribute to these processes that result in isoprene and DMS production? Some information from the phytoplankton cultures that we looked at. Just a big table here. There's isoprene on the left, DMS on the right, and then normalized rates of production to organic carbon into chlorophyll A, organic carbon and chlorophyll A. So I just want to walk you through the data very briefly. Many of the phytoplankton did not show any production, and there was no significant production at all in these, but some produced quite a good amount of isoprene, particularly the cyanobacteria seem to be strong producers of isoprene, but also some cryptomonads we found. And then we get DMS production in chlorella, green algae, and one of the cyanobacteria that didn't produce isoprene, but produced DMS. And then there was one Cenedesmos chlorophyte who produced both of those in significant amounts. So there's quite some diversity there. Not all of the photosynthetic organisms, phytoplankton, make these compounds, and not all of them make them at the same quantities. Okay, then I want to come to our diurnal study. On the top here, you get the first figure. There's time along the x-axis, and then we've got the aqueous isoprene and DMS productions in picomoles per liter. That's the pinkish line and the blue line here for the DMS. And then the atmospheric isoprene in parts per billion in this orangey line here on the top. So these are the measurements that we've done from an early morning start and then sort of an evening finish all throughout that one day. And then we can use that information to look at the fluxes. We were interested in, does isoprene go into the lake? Does DMS go into the lake? Does it come out? That's an important question, of course, to ask. And to be honest, the initial idea, the hypothesis really was that it's likely because isoprene is so strongly produced by many of the green plants that you see when you look out of the window, particularly poplars, willows, quite common around Lake Constance. They're really strong producers of isoprene that we thought that the atmospheric concentrations would be so high that probably the lake would act as a sink. Because the water, there's very little isoprene, little DMS, it won't go. But when you do the calculations, and we use wind speed and temperature data to do that, it appeared that both isoprene and DMS came out even during the day when the concentrations in the atmosphere are really quite high. And what you notice here is that I didn't plot temperature and sun and light concentrations in this particular figure here. That B panel is missing, but it's basically when the sun comes out, then you get suddenly a burst of isoprene being released from the terrestrial biota or the isoprene producing trees. But as soon as sun sets, then very rapidly the isoprene disappears. Isoprene has a very short half-life in the atmosphere, only a number of hours typically, and it reacts very rapidly with OH radicals in the atmosphere that are produced due to photochemistry processes. So it was really quite interesting that even at the time when isoprene production is high in terrestrial environments, the lake still releases both isoprene and DMS into the atmosphere. So biogenic volatiles affect atmospheric chemistry and climate. I showed you that for DNS already early on. Freshwater systems are woefully ignored for the production. It's again, it's a new playground opening up for us there, and I think it would be quite interesting to do a little bit more on that, particularly when it comes to us pushing northward, where climate change has such a dramatic effect on the biology and productivity of freshwater systems. They're constant as a source of isoprene and DMS. It's not just saying that was a really important finding, I thought. Production is closely linked to the phototrophic process. We show that, you know, phytoplankton algae can release that. That brings us to the next step here, where we started looking at macrophytes, myriophyllum, and we found that they also quite strongly produce isoprene. We found a few days ago. That was interesting first finding, really. And biome fluctuations suggested a possible physiological role in environmental acclimation. So, because both of these compounds, DMS and isoprene, they are involved in stress reactions in phytoplankton and seaweeds, we think that, and in higher plants as well, we think that, you know, there's a role for them when aquatic plants get under stress, for them to use these compounds to react to the presence of reactive oxygen species. So what are the possible consequences? That's the next step, really, that we want to address in the near future. The nighttime release of isoprene has implications for atmospheric cycling, because the lakes, basically, they function like a charged battery. They get charged with isoprene and DMS during the light period, which doesn't come out very rapidly, whereas terrestrial production of isoprene shuts down when the sun sets, and that isoprene is quickly degraded. So there's a chance, possibility, that if there's high wind during the night, that you know, increases the exchange of isoprene with the atmosphere, and suddenly you've got isoprene appearing in the lake air, in the vicinity of the lake at night, which would not happen in a truly terrestrial environment. So that's interesting to look at, and I want to give you a bit more detail on that in the next slide. And freshwater systems are increasingly important source towards the pole. So that comes back to the question of linicity, you know, how the linicity may have an effect on the overall isoprene that we measure in the atmosphere in northern environments. So that's the isoprene. Now coming back to that scenario early on, we see that during the day it's being produced, particularly by, you know, willows and poplars on the right there, but also by photosynthetic organisms in the lakes. Then when it comes to the night, this is very quickly degraded by OH radicals. But since the lake acts as a source of further isoprene and the OH radicals are being consumed already, and I should go back one quick step actually, I want to talk a little bit more about the OH. So one of the main interests also on isoprene is the fact that isoprene and methane, a very strong greenhouse warming gas, as you all know, are in competition for OH radicals in the atmosphere. So the drawdown of methane, the destruction of methane, is in direct competition of the drawdown of hydroxyl radicals from isoprene. So the more isoprene there is, the longer the half-life of methane in the atmosphere. So larger warming potential as a result. Right? So the more isoprene comes out, the longer the methane survives, the more warming we have. So, but now the isoprene is coming out at night as well, and that changes the atmospheric chemistry, because it's likely that because the OH radicals are gone, that they then react with isoprene nitrates. That has further complicating, is a further complicating factor for the atmospheric chemistry and the formation of particles in the atmosphere as well. So that can result in these very harmful small particles, what I call PM 2.5, which people then breathe the next day, and so it has a direct health effect. Particularly in areas like this where you've got a lot of human beings, a lot of people living around the lake, a lot of production of these nitrite radicals in the atmosphere due to burning of fossil fuels, of course, and that can stimulate then the formation of particles the next day, which may be harmful. If you're suffering from asthma, etc., you may feel. So I talked to you about the first part of possible consequences. And then the second part, going northwards, this is some data from Riikka's group, and you can see the data for isoprene in the column here. You see that subarctic environments are relatively high isoprene producing environments. The further north you go, lower Arctic and then up into the high Arctic, the isoprene production becomes less and less and less. Right, so the terrestrial production of isoprene goes down. If we're assuming that the productivity of isoprene, or the productivity as a whole of northern lakes is similar to what we find in Lake Constance, you can do this quick back of an envelope calculation. So I've done that here for the Lake District in the UK, where we've got a linicity, a lake area cover of only 3%, although it's the Lake District, right? The contribution of isoprene from these freshwater environments from the Lake District is only about 2% to the total isoprene in the atmosphere. If we're going further north, the Rinnan example here, where the linicity is already 13%, so a lot higher, the contribution already comes out at above 80%. So the total amount of isoprene that comes from these freshwater environments provides 80% of the total isoprene in the atmosphere. That's really quite interesting. Some areas in northern Canada, they've got a linicity of 50%, so it's huge. It's even 5 times higher than what we have in Greenland. So it's really quite interesting to look at, isoprene that's coming out from these freshwater systems. So that's just a schematic model of how this works. From temperate Lake Constance, UK Lake District to southwest Greenland, we get more and more lake production of isoprene, less and less terrestrial, and at some point, of course, the lakes become more important in overall isoprene production than the terrestrial ones. That's a conceptual sort of idea, but we haven't tested that. We don't have the data for that yet. So we'll summarize all of that and then finish up. Freshwater isoprene and DMS fluxes are poorly documented and unaccounted for in biogeochemical and ecosystem models. When it comes to freshwater systems, of course, only, not so for terrestrial environments. The linicity in the Arctic is very high, up to 50%. Freshwater flux may be greater than terrestrial emissions in the Arctic. We don't have the data yet, and this is one of the most important reasons, I think, why we're here, because Riikka uses technology to enable the storage of isoprene onto these cartridges, which she can then analyze in Copenhagen using the GCMS system, which I cannot do. And in the high Arctic, we do not have power, we do not have a GC, of course. So Isabel wants to take these cartridges into the high Arctic in July and August to get the first water samples analyzed for isoprene. And if it comes out that, yes, these environments are really quite important for isoprene, that's really quite important finding. But we must intercalibrate, or we must understand that these thermal absorption tubes actually work quite so well for these aquatic environments as they already do for the semi-aquatic and terrestrial atmospheric environments that Riikka has been working for many years with. So this would have implications for Arctic climate and atmospheric chemistry. Isoprene nitrates I mentioned, which might be an interesting sort of chemical compound that is being produced due to the nighttime release of isoprene. So I want to thank you all for your attention. Once again, it's really great, fantastic to be here. Lovely to spend the summer with you, and I'm looking forward to any comments or questions that we may have. Thank you very much. Also to take questions from the Zoom people. If you want to put something to chat, or if you just want to open up your microphone, that's all fine. Are there any questions? Or are you saturated?
I have a question until. Okay. Well, the stress, the light, what is stressful of what I understood and learned is that it's UV that is most stressful. but UV can go through clouds, so I wonder how it can really help.
Ah, okay. Well, but there will be absorption of UV light. So if you've got a clear blue sky, the sun is still the same energy, you get a lot more UV on the surface of Earth. If you've got cloud coverage, the sun is still the same energy, you get a lot less UV light on the surface of Earth.
Yeah, when you have a thick cloud cover, you will have less, but if you, I saw studies showing that if you have what is this type of nice white big cloud,
Yeah.
it increase in fact the amount of UV light received at the surface of the
Okay.
Earth because of some kind of reflection
Reflection,
and
yes.
diffusion and.
I mean, I don't know a lot about UV, to be honest. I've never studied light photophysiology to that depth. But I would think, again, the absorption of UV light is quite strong in water. So it will not reach quite that deep, I think. You know, you can see that in profiles from the sea that there's no UV light, a few meters down, and even a few centimeters into the water surface. Water droplets will absorb a lot of UV as well. And I think due to the fact that there's reflection in the clouds itself, the path, of course, is longer. For the chance for UV being absorbed on that path, on that route from the sun to the surface of Earth, is a lot higher because it's more diffusive. So I don't know whether UV light really, I mean, it might be true that UV light is increased in a slightly overcast.
Or not that much reduced if you have little clouds, like
Yeah,
a few clouds over a patch, like it
yes.
wouldn't help, I think.
Yeah. So, yeah, but it's interesting because we believe that light is a main driver because it results in the production of reactive oxygen species inside the cells. You know, we get skin cancer as a result of that because these reactive oxygen species, they can very quickly react within, nanoseconds, I believe, with anything that is organic, and that destroys our DNA, and hence you get cancer as a result. You get mutations as a result of that. So we believe that isoprene, particularly also DMS, is produced in response to this UV stress and the following chain of reactive oxygen species that's being released to then provide organic nitrates, basically, that these reactive oxygen species can react with. So rather than damaging your DNA, it rather destroys the DMS or the isoprene, and hence keeps or reduces the probability that the DNA is being damaged. So
Okay, so that's the physiological role of increasing your production.
Yes. So for DMS, there's clear data that reactive oxygen stress would increase the release of DMS. So we know that there's lots and lots and lots of DMSP inside many algal cells. It's a very important component of the total organic molecules inside seaweeds, for example. And that's very steady. Nothing's happening to that. Once you apply some stress, there's an enzyme system that then reacts with the readily available substrate and releases the DMS inside the chloroplast. So it floods the whole chloroplast with DMS to protect then the whole structure, the membranes from the damage of reactive oxygen species. And of course, part of that diffuses out of the cell as a waste product, basically.
Michael, you have a question here from Ilan?
Okay, good. Go on.
Ilan, do you have your, okay, it's okay.
Yeah, I don't know if you can hear me.
Yeah,
Yes, it's okay.
Okay, cool. Yeah, thanks, Michael, for the great talk. Yeah, I just had a question on why is the aquatic flux so large compared to the terrestrial flux in the Arctic? Is it because of, you think there's a temperature inhibition of emissions from the trees there? Or is it because of the vegetation type or the scarcity of vegetation there, or a combination of both?
Yeah, so I mean, it's a good question, and my thinking when I came up with this model or with this idea that you hopefully see on the screen now is that vegetation becomes less and less and less the further you go north. Riikka has shown that it becomes like a cold desert ultimately. So vegetation processes, terrestrial vegetation processes are relatively small. So just the opportunity for ice cream being produced in that environment is a lot smaller than in a tropical forest or in a temperate forest, where we are. So the ice cream release into the atmosphere, the further north we go, becomes less and less and less. The assumption then is that the ice cream release for these productive water bodies would not change quite so much, because we still get macrophytes present in these ponds in northern Canada. We still get blooms, and we're worried about cyanobacterial blooms in northern lakes now, which may affect the water quality, and particularly the Inuit, the local population is affected by the toxins and all that. So we have this changing environment, which results in the release of nutrients as well, humic acids, organic molecules from the melting permafrost into these lakes, which then stimulates productivity. So there is a fair chance that the overall productivity of these northern lakes, and hence the release of isoprene, is quite similar to the amount of isoprene that we already see in Lake Constance and possibly also in Lake Geneva. So we believe that the further north we go, the lakes, basically the production stays steady, but relatively their importance increases due to the fact that terrestrial production just becomes less and less and less the further north we go. So that's, I think, the general idea behind this whole model that you see in front of you.
Yeah, great, thanks.
Okay.
Okay, thanks a lot for this great talk. I'm really interested also in the production of GMSP by seaweeds. I did my PhD on metabolomics on brown seaweeds.
Okay.
And for me, GMSP was one of the most interesting components, because you can really see that there is a temperature on light.
Yes. So even in the brown seaweeds, you say, because brown seaweeds typically are relatively low producers of DMSP in comparison to the reds and the greens, which are massive producers of DMSP.
For the greens.
Interesting.
But even for the brown seaweed, there is this production at the surface of the seaweed. And recently I've done with some collaborations with other people in the world who collects brown seaweed everywhere in the world. And see what were the difference of the different main chemical families produced by the seaweeds, depending on the temperate and tropical regions. So we did some metabolomic studies on this, and the first biomarkers of the difference between temperate and tropical regions were the GMSP.
Okay.
Among like thousands of compounds, the first one was the GMSP.
Yes, yeah.
It was more produced in temperate regions compared to the tropical regions.
Yes, yes.
And for me, it's really, I don't really understand, because for me, the GMSP also produce the antioxidants, the UV stress, and there is for sure more UV stress in tropical regions. So I cannot really explain why it's more produced.
So that's an interesting question. One of our PhD student has looked at it a few years ago when he went to tropical environments. And I think the general idea, and there's also an interesting paper by Dani and Loreto on this, Francesco Loreto, where they suggest that ice cream is relatively more important towards the equator, and DMSP is more important the further north you go. One of the most highly DMSP producing environments that we know of are these brine channels inside the ice, so where the diatoms are being frozen into. And they use DMSP as what is called a compatible solute. So you basically, because the brine channels, the name gives it away, brine, there's a lot of sodium chloride in these channels, because it's the water, the H2O, that freezes out, and it leaves the sodium chloride behind. In these channels, it's a very dense, highly sodium chloride enriched environment. And sodium chloride is toxic to many enzymes, to many metabolic processes. So what these ice diatoms do is they produce a lot of DMSP in order to use that as a compatible solute to drive out the sodium chloride, just by pure fact that there's no space for the sodium chloride anymore, it dries it out. So rather than using an active pumping mechanism to get rid of the sodium to the outside, they increase the amount of DMSP, which doesn't diffuse through the membranes, it's being kept inside, and then that detoxifies them from the soil chloride. So the further north you go, there is some effect of that, cold, temperate water where these organisms want to protect themselves and their enzymatic functioning using DMSP. That also has been shown for temperate algae, I believe, some work by Ulf Carsten and others in Germany, actually, University of Bremen, where they show again that the colder the environment, although it's not the freezing environment, the amount of DMSP goes up. And the belief is that the DMSP helps with the what do you call that, the tertiary formation of the enzymes, the spatial structure of the enzymes, so that they can function properly, because they resemble water and can make metabolism still continue to work because the enzymes are still functioning. So that's why even in temperate waters you see more DMSP in these so-called environments as well.
Yeah, it's also known as a fire protectant.
Yeah, as a fire protectant, exactly. Yeah, compared to solid and fire protectant. That's right. So DMSP is like a multifunctional compound.
Yeah,
It does a little bit of everything, it seems. It's odd. And another line of research that I haven't mentioned in my talk today, it was very interesting because Riikka mentioned it earlier. All these volatiles are given off in the atmosphere. They are really important into chemicals. They lead organisms to plants that are infected with the herbivore, because the volatiles change. When the herbivore eats on the plant, the volatiles change, and then the predator comes in, the carnivore, and eats the herbivore, which is a tritrophic interaction, we call it that. So it's really quite interesting. Again, very little known about that in aquatic environments. All these aquatic environments produce these volatiles, and we know that myriophyllum is just, there's lots of different volatiles given off in different conditions. Pulse here, pulse there. What does that mean in terms of information content that other organisms then can pick up on? So that's really interesting questions. And we know that seabirds, they use DMS as a directional cue to find areas of hyperbaric productivity. The albatrosses on my first schematic that I showed early on, albatrosses have very well developed noses, and it's a featureless environment. All they see for weeks and weeks and weeks is just the ocean. There's nothing on the horizon. And they still need to feed their chicks back on the island, basically, and they need to then migrate or move to these areas which are high productivity, where there are krill swarms, for example, to exploit them, and then fly back the krill to the nest, basically, to feed their chicks. And they use the DMS that's been released by the knowledge activity as a direction cue to find these areas. So very interesting for chemistry there.
I think you answered them.
Okay.
Yeah.
Okay.
So I was wondering about the effect of atmospheric CO2 concentration, that you showed that the DMS production, it decreased with elevated CO2, right?
Yeah.
And it's kind of in agreement what we know from the terrestrial environment, that isoprene production decreases with the elevated CO2. Do you know if the isoprene production in the aquatic environments also responds the same way? And is it what is the mechanism behind the DMS response?
Yeah. So I do not know that there is no, as far as I'm aware, there's no information. So CO2 increase and ocean acidification experiments, that's what we call that. They've been very common, 10, 15 years ago, and people have moved on from that. I don't think isoprene has been properly addressed in that, but I may be wrong on that. But I guess the mechanism would be that if you provide more CO2, there are some benefits, of course, to all plants, because CO2 is a substrate to keep photosynthesis running. So as long as you can manage your photosynthetic apparatus, the Z scheme, to function, and you put in more CO2 and it functions nicely, you do not need to worry about the amount of light quite so much. So the overspill of too much light hammering your pigments results in the reactive oxygen species that are given off. So as long as the CO2 can promote the flow through photosynthesis, the chance of reactive oxygen species being produced is relatively small. So I would think that that may be one possible mechanism that could be explored as to the reason why there's less DMS and why there's less isoprene as well, if you increase the CO2. Right? So CO2, yes, a warming effect, which might be bad, but there's also benefit that you get more productivity because CO2 is the substrate.
And maybe just to follow up there, did you have like a control that it was not the pH effect, but the CO?
So the pH effect we did not look at. You say that, what happens if you change the pH but not the CO2, if that's the question. We did not do that in these sort of experiments. It's more driven by just exploring, what would a future climate or what would a future atmosphere, what would that mean to the release of these gases? And again, it's not so much, sometimes we confuse production and concentration. Quite often it's concentration measurements that we're doing, not production measurements, right? So what the net and the gross is, we also don't know. So that's another black box that we haven't really opened yet. We just see what's coming out without really understanding what's going on, right? We haven't measured that.
Yeah, I mean, maybe it's a serious question, but you spoke about isoprene and the influence of nitrate, didn't you say that?
Yes.
How, because the lakes you looked at in Lake Constance and here, they have quite little influence on agriculture. I wonder if isoprene would be different in a place where freshwater lakes are near aquaculture. Aquaculture, yeah. There are lots of fertilizer going into the lake, and that would actually feed the nutrients, and you would have more production going on in the lake.
It's a good question. It would be interesting when you think about salmon cages. What is when you do transect across the salmon cage area of marine aquaculture? How would these volatiles change? It would be interesting for various reasons. Obviously, what's the effect on the environment of these mariculture activities? What might be the effect of the volatiles on the parasites that are infecting the salmon skin? The copepods that suck on them, and all sorts of things. I think the main concern for us in our work at the moment is, aquaculture would be one source of nutrients, as you mentioned, and permafrost smells would be a source of nutrients. How does it change the biodiversity? And what does that mean, that biodiversity change to the overall production of these compounds? So it's more the question of, does it shift to cyanobacteria? How worrying is, because we get cyanobacteria blooms when we have a lot of phosphorus in the lake, because again, draw down the nitrogen and you stimulate the cyanobacteria. And because we showed that cyanobacteria are quite strong producers of isoprene, that may then change, of course, the production of isoprene in the lake waters. So it's more like a secondary effect rather than a direct effect on the gases. It's more secondary effect, they release nutrients, and hence you get a change in the environment, which then results in possible changes in the output of the gases. Good. Any other questions? No?
Thank you very much, everyone, for your participation and questions. And
It's back to Genevieve.
yes, Genevieve.
Yes, online, is there any remark or question? Nothing more in the chat, so I think it's okay for us there.
Yeah. Okay. So yeah, in a half hour or so we can join at the chateau to have a little drink and chat more.
Good. Okay.
Thank you, everyone.
Thank you, everyone. And I think the presentation will be very nice for the CARRTEL YouTube channel.